Hello and good morning, madam. I'm Muhammad Afirifki with my groupmate Aaron Rodik Lakra and Baldwin Raj. We are going to present our project, which is basically the programmable MOSFET coprocessor using the Q16.16 fixed point architecture. So basically, our project is about solving the MOSFET saturation equation using digital hardware. So instead of using software calculation, we designed a hardware system that can calculate the drain current directly. So we use a finite state machine and data path design method to build a reliable and fully tested system. It's finite state machine plus D. Okay, next. So basically in software, the MOSFET equation is usually solved using floating point calculation. However, floating point hardware is very large and uses many logic gates. So to make the design simpler, we use a Q16.16 fixed point format. So the calculation are performed over multiple clock cycle instead of all at once. Although this makes the computation slower, it greatly reduces the hardware size and power consumption. So basically that's our problem statement lah. So this is our top-down FSM plus D and data path methodology. So the design is divided into two paths, which is the control unit, the FSM, and the data path. The control unit is where we control the order of operations, while the data path perform the actual calculation. Only one multiplier and one divider are used in the design, where the FSM controls when these units are used, allowing the hardware to be shared efficiently. And then we can see our bottom-up modular design, although the overall system was planned from the top level like before, but the modules were built actually from the bottom up. We first designed the basic components such as registers, multiplexers, and the constant ROM, and then the small modules were then combined to create the arithmetic unit, which is the ALU, the multiplier and divider. And finally, all the modules were connected in the top module, which is the top.v. So storing the technology constant in the ROM also makes it easier to update the design in the future, as we can see in the constant_rom.v. So the system uses a 32-bit Q16.16 fixed point format to represent the decimal values. So the numbers such as voltage and device parameters are converted into fixed point values before the calculation begins. So when multiplication is performed, a 64-bit result is generated and the middle 32 bits are selected as the final result. This allows the system to perform decimal calculation using digital hardware, because as we know, binary cannot be converted into point like straight away. We need to use the Q16.16. So I'm gonna hand over to Raj for our results.
So for the hardware reuse, one important feature of the design is the hardware reuse. Instead of using several multipliers, the system uses only one multiplier for all multiplication operations. The finite state machine controls which values enter the multiplier at each clock cycle. This reduces the amount of hardware needed and saves the FPGA resources. So for power optimization, the system can also avoid unnecessary calculations. For example, if the transistor is in the cutoff region, the drain current should be 0. The hardware detects this condition early and skips the remaining calculations. This reduces the number of clock cycles used and lowers power consumption. For error detection, a good digital system must be able to handle invalid inputs. For example, if the channel length is equal to 0, division by 0 would occur. The system detects this condition before the division operation. An error flag is generated and the finite state machine enters an error state to prevent incorrect results. So for the verification results, the test bench was used to verify that the calculations are correct. The PMOS constant stored in the ROM is set to be half of the NMOS value. Therefore, the PMOS current should also be half of the NMOS current. The simulation results confirm this relationship, showing that the fixed point calculations are accurate. The final project outcomes. In conclusion, this project successfully implements the MOSFET saturation equation in digital hardware. The design also uses hardware sharing to reduce area, skips unnecessary calculations to save power, and includes error detection to improve reliability. The modular design and simulation results show that the system works correctly and meets the project objectives. And now I pass it to Aaron to explain the results in the waveform.
Okay, so now we will be moving on to the simulation part of our project. So in total we have 4 Verilog files. So the first is the data path Verilog file. So this is the total Verilog data path file for our project, and the control unit path, the Verilog file, and the top module Verilog file, and then the test bench for our total digital system. And then actually we simulated the whole system in Visual Studio Code using an extension to view the waveforms, and the Verilog files were simulated in Visual Studio Code, and these are the commands that we used to simulate the Verilog files, that is using the Icarus Verilog extension. And then we got the VVP file from our terminal, and then using that we generated the vcd.vcd file, and that shows our waveform. So these are the different test cases that we tested for. So first we tested for NMOS normal operation mode, and then we tested for PMOS normal active mode, and then third is the NMOS cutoff mode, and then for the fourth one day we tried to confuse the system by basically giving the length for the transistor to be 0, and then the hardware actually bypassed the calculation by detecting that the length is 0, so that is not valid. And another exception, the width, we set the width for 0, so even for that our design calculated it as an exception and safely came out of the loop, and no calculation was done. So these are the values for the NMOS, the PMOS, and the NMOS cutoff that we did, and this is the waveform that we have. So we have the clock signal. So going from first, we have the start signal, reset signal, error, if it is division by 0, for example length or any for example length or the width, if it's 0 then it comes out of the loop. And then we have clock, we have the done signal, and then this is the current out signal that we have. And then we also have the current state. So in total our FSM has 22 states. So using a 5-bit signal, it actually shows how many in what state it is in. So these are the states. So for example, if I show the current state, so it goes all the way up to so as you can see the number of states is varying. So yeah, and then this is the signal for it shows the length of the transistor, this is the width, and this is the temporary variable to store our calculation in the ALU, and this is the secondary, this is for the current, and this is for the gate source voltage, and this is the product signal, and this is the quotient signal for the ID current equation calculation according to what we can calculate. And as we can see, the simulation goes accordingly according to what values we give for the current equation, accordingly like what voltage values that we set, for example threshold value, and for example what length or width that we give for our NMOS or PMOS transistor. So based on, if for example if it is a NMOS transistor, it will use a specific formula, and if it's a PMOS, it will use a specific formula according to our design. So this is the simulation, and according to the simulation, as you can see, the current state is if the digital design determines that if it needs to go back to a certain state, for example calculation of squared value or division, or for example add or a minus operation, it can switch accordingly. So as we can see here, it's in a higher state, then it goes back in the current signal, we can see. Yeah, so this is the calculation, and the current equation and the current signal actually shows the total current output of the current, and also if it's done, the signal will be showing done, and then the done signal will go up, and then the output will be out given out, and then as we can see, for so this is almost the end of the simulation, and as we can see, this the end of the simulation, we did the exception, and as we can see, the for this one the current is 0, and for the previous one here we got the ID out to a certain value. So this is this is the video presentation for our digital system design that we did for a calculation of the current equation for NMOS and PMOS. Thank you so much.